Okay, good morning everyone. Welcome to the first day of our school, TPI, I think TPI school on QFT and holography or something like that. I'm Jakob Polweg, I'm one of the organizers. The other two organizers are Katharina Wölfe, maybe wave, and Federico Capone. Yeah, very good. If you have any questions about the school, just approach us. If you need general information like the schedule, it's online on the Indico page, as you probably have found out already. Yes, we're going to start today with the first lecture on entanglement in CFT and holography. Our first lecturer is Nele Callebaut from Cologne University. We're very happy to have her here, and yeah. Thank you.
There we go. Thank you. So thank you very much to Martin and to all the organizers for inviting me and hosting me here in Jena. It's my first time here in the city. So yes, I'm going to talk about entanglement in CFT and holography, and this will be based on a review that I put on the archive last March. So I can give you the archive number. So I'm going to follow the structure of that review, but add some more details. Okay, so the lectures will be about entanglement in CFT and holography. So there's two parts. And so this review paper that I'm referring to is this number, 16827. Okay. And so this will naturally split into two parts, and I'll start with entanglement in CFT. So let me get rid of holography. Do you have like a, yeah, and I prefer if it's dry. Yeah, this will work. Okay. So we start with entanglement in CFT. And I wanted to start with a section on wave functionals and density matrices. Functionals and density matrices. So here what we'll discuss is the relationship between path integrals and states. Okay. Between path integrals and states in quantum mechanics and then by extension in quantum field theory. And that will lead to a pictorial notation for wave functionals and density matrices, which we'll use very heavily throughout the lectures. So I want to go carefully over this. And this is a part of path integral formalism that is not always emphasized in a standard course. So the best reference for this, so I'll try to give references. If I forget, you can let me know, or you can check it in the review. So the best references for this, or the ones that I'm following now, are Polchinski Appendix A and Hartmann's Quantum Gravity Lectures. Okay, so as I said, let's start with quantum mechanics, and then we'll jump to QFT later. So let's start with a quantum mechanical system. So I'm going to write down a quantum mechanical system, so a Hamiltonian of Q and P. And I'm going to follow Polchinski here in adding the hats on the operators to distinguish for this section the operators in the Heisenberg operator formalism from their role in path integral formalism, okay? There's no telling when I will start dropping the hats, but in the next section probably. Okay, so we have our quantum mechanical system, so I can take position eigenstate Q. Okay, so this is position eigenstate. And I can act on this position eigenstate with Hamiltonian evolution. And this will now give me a state that depends on t. And this is what is called a Heisenberg eigenstate. So if this one was a t is 0 Schrödinger position eigenstate, then this one is called a Heisenberg eigenstate. So meaning, like this one, that if you act with the time-dependent, in this case, Heisenberg operator, on this state, you will get out the eigenvalue q. Okay. So where q is now your time-dependent Heisenberg operator. So let me get the signs right. Okay, I already had a sign wrong on this here. Okay. So this now being your Heisenberg operator, which in Heisenberg formalism is time dependent. Okay. Now let's consider a transition amplitude. Probably I go to the next board for this. Okay, so we consider a transition amplitude from starting at some initial position qi to some final position qf. This would be your transition amplitude in the Schrödinger picture. I want to write it down, the same thing, in Schrödinger, Heisenberg, and path integral formalism. Okay, so here I have Schrödinger. This is my amplitude. Right, this thing. Let me evolve over a time period which I'll call large t. Okay, I had a small t here, but I want a transition amplitude from a position qi at t is 0 to some final position at some finite time large t. Okay, so in Heisenberg notation, this would be this transition amplitude, just using the Heisenberg state that I have on the previous board. So this is, in the Heisenberg picture, my amplitude. And the point is that this is exactly a path integral, equal to a path integral, where you integrate your action, and you path integrate from qi at time 0 to qf at this time large t. And I add that the action is the integral over time of your Lagrangian of q dot. Sorry, it's just a bit in the way for my, I'll erase this here. Okay. Okay, so we have Schrödinger, Heisenberg, and path integral version of an amplitude. So basically, the transition amplitude is given by the path integral. And So the thing I boxed now is what will allow us to understand the relation between path integrals and states. So let me sketch how you derive that this amplitude is equal to a path integral. So this will be a repetition, but there's a reason why I sketch the steps, okay? So for the details, again, you go back to Polchinski. But roughly what you do is this. The first step is that you insert a complete set of states in this Heisenberg amplitude. At some intermediate time t between 0 and large T. Okay? So what you do is you write this left-hand side as dq of qft, qt, qt, qi 0. Okay? So what you see appear is these products of Heisenberg amplitudes. And so you just repeat the step instead of just at one time in between your initial and final time. You do this many times for infinitesimally close time intervals. Okay, so you insert a bunch more of complete sets of Heisenberg states, and then you'll get a product of integrals over Q and Heisenberg amplitude at each for each factor, okay? Okay, where here what I mean is the amplitude that is an epsilon apart in time. So if I write it now in the Schrödinger form, I would write this. Then I insert more complete sets of states, and this time momentum eigenstates. So basically, so far what we've done is we start with inserting a complete set of Heisenberg states at some intermediate time. We do that for a bunch of intermediate times in your amplitude. You insert a complete set of momentum eigenstates. Now you use the plane wave formula for writing out what these QP contractions are. So now let me try to squeeze it on this one board. Okay, now I'll have to go to the next one. Which means I press this button. There you go. Yeah, I think it will work. Good. So finally, what we have is product integrals over the Q's, the P's, and these product integrals is what limits to a path integral. So this is what is understood by a path integral. It's this limiting procedure of these product integrals. So we end up with a path integral. First, a Hamiltonian path integral. So let me call this a Hamiltonian path integral, meaning what you end up with is a path integral over all possible paths from the initial to the final state. All possible paths in state space. Okay. And then you integrate out this P to end up with what you usually write as the path integral, which is the Lagrangian path integral. Like this, where now you're path integrating over all possible paths in configuration space, Q. So this is the Lagrangian path integral. Okay, so this was to sketch how you rewrite the Heisenberg amplitude as a path integral. So this is basics. The main reason that I'm repeating this the sketch of the derivation is precisely because of the first step in the derivation, which was adding a complete set of states, because this shows us the concept of cutting and sewing path integrals. And this is what will come back in this pictorial notation very often. So let me repeat here this first step of the derivation. Which was just the insertion of a complete set of states at a chosen intermediate time, small t. Okay. Okay. This shows us the concept of cutting and sewing path integrals. So let me explain how. The point is that now, by having sketched the derivation, we understand that each of these Heisenberg amplitudes is a path integral. So on the left here, let me use some short notation. We have a path integral over a time interval 0 to large t. And you can write that one as some ordinary integral over positions q of a path integral from this intermediate time t to the final time times a path integral of 0 to t. Okay, and so this means you can read this from left to right or from right to left. If you read it from left to right, you can read it as cutting your path integral. If you read it from right to left, you can read it as sewing your path integral, or actually, most of the time, I will call it gluing your path integral, okay? So basically this, so if you read from left to right, we see that by inserting a complete set of states at some chosen constant time, what you've done is you've taken the full path integral from 0 to final time, and you've cut it at some intermediate time into two separate path integrals. Okay? So you cut path integral to 0t tt. And so this procedure gives rise to a Hilbert space representation of your given amplitude. Because it gives rise to a description in terms of states qt. So it's a Hilbert space rather than path integral representation. And sometimes you can cut your path integral in different ways. And this will give rise then to different Hilbert space representations of your amplitude or your path integral. Right, so this is reading from left to right. If you read it from right to left, you do the opposite operation, which is taking two pieces of path integrals, putting them together, and gluing them into one path integral. And so to do that, you take the position at the final time of your first path integral to be equal to the position of the first time of your second path integral. So you equate the q at t, and then you integrate over all possible q's. And so this means that you've allowed your q at t now also to fluctuate everywhere, so you've successfully glued your path integrals into one. So equating the q's at t and integrating over them allows you to glue path integrals. All right. Okay, so what we've discussed is for amplitudes, and most of the time we'll be working with the Euclidean version of those, so Euclidean amplitudes, in which case the exponent will not have this oscillatory behavior. So let me write the same statements for Euclidean amplitudes. So the Euclidean amplitudes are defined by analytically continuing your Lorenzian time. So taking t to e to the minus I theta some phase times t, or you can write this as setting t equal to e to the minus I theta some new real parameter u. Okay, and so what this does for you is it rotates your contour. If you were integrating in your action over real time, maybe this is the time where I start using my colors. So if you were integrating over real time, then this rotates the contour to integrate over real u. If this is the angle theta that you rotate over. Okay, and so specifically, if we take this angle theta to be pi over 2, then we have t equal to minus iu. And so in this picture, then we'll have that instead of integrating over real time, we're now integrating over real u, where real u is equal to minus the imaginary time. Okay, so this u that we've introduced is Euclidean time. And if you just redo this, this path integral derivation for these Euclidean amplitudes, you'll find the analog statement, which is that your Euclidean amplitude, sorry, no i's, integrating over some distance large u in Euclidean time small u, is equal to this Heisenberg amplitude is equal to the Euclidean path integral starting from qi at 0 Euclidean time to some final position qf at final Euclidean time u. Right, and so I'm going to introduce this notation I for the Euclidean action. So to be consistent with the reference I gave for the notes, where minus I is given by this Euclidean Lagrangian integrated over u, which is equal to this in terms of the original Lagrangian, okay? But roughly, it's just setting t equal to minus iu in all of your formulas will lead to everywhere where you had an IH to a minus HU. I'm still a bit worried about this sign. Good. Let me write this part. So again, this boxed part or this underlined part for the Euclidean version is the statement that will allow us to understand the relation between path integrals and states. So to go there, first, I'm going to change the notation just a little bit, that I start integrating from minus u, and I integrate to Euclidean time 0. So of course, this is the same. I'm integrating over the same interval of time in the end. So I'm starting just now from minus u, ending in time 0, dq e to the minus I over h bar. Okay. So that means I go to the next board. Links. Yeah. Okay, so now we're ready to understand the vacuum state as a path integral. Okay, to do that, we start from this. Let me not repeat it. So we start from this line, and we will do two tricks. The first one is to insert a complete set of energy eigenstates in here. So let me write that. This is the first step, and then the second step is to take the limit of u going to infinity. So take u to infinity. then this whole sum will just be dominated by the lowest energy eigenstate. So in the exponential, only the zeroth contribution of the energy will contribute. All the rest will be too suppressed. Okay, so we only have one contribution left, which is the one from the zero energy state, which I'll write as 0. Then what we have 0 Qi, and some factor here, which is the zero energy times infinity. So what we see appear here is the vacuum wave function, which we can write as psi of Qf. So I could write here 0 to remember that it's the vacuum state. But because in most of the lectures, when we write psi, we'll be referring to the vacuum state. I'm just writing psi, okay? So we see appear here the wave function psi of Qf, and then the rest, what we have here, are basically just numbers, which are independent of Qf, and therefore not too interesting to us. So this one and this one give us some Qf independent factors, just numbers. They're just numbers, okay? So what we found, let me write it in the new line, is that psi of Qf is equal to, let me bring back the right-hand side. I was just rewriting the left-hand side of this last line on the middle board. Actually, for the recording, it would have made sense that I repeated it, but okay. If I bring back the right-hand side, now that I've rewritten the left-hand side into this, the right-hand side is my path integral from Qi at 0, at minus infinity to Qf at 0. Okay, I think now it's time that I drop the H bars. This was just to emphasize that what is the factor that weighs each path in the path integral, which is e to the is over h bar. Okay. Good. So what we found is that the vacuum state, or the vacuum wave function, is proportional. I use here a proportionality sign because I'm dropping these numerical factors that I'm not interested in. It's given by the path integral from going all the way from minus infinity in Euclidean time to 0 Euclidean time. So I can spell that out and say this is Qi at t is minus infinity and Qf at t is 0, where now I'm using the notation Euclidean time for this u that I introduced. I didn't do that before because we'll do this analytic continuation in some other cases as well, so I wanted to keep this quite general in terms of a general coordinate u that you introduce. But here, let me actually call it Euclidean time. Okay, this wiggly sign is because I removed these numerical factors. But if I just define this as the wave function and say this is the unnormalized wave function, I can bring back my equality sign. Okay, so this is my unnormalized wave function. So a wave function in quantum mechanics, you know, is the contraction of a state written as a cat with some bra QF. So if I've identified in path integral notation what this vacuum state is, I've now also identified what a cat psi or a state psi is. Namely, it's this path integral that I integrate to the 0 Euclidean time slice, but I should leave open to what position I'm integrating at that time. So I'm leaving this here, I write this as a dot at TE as 0, meaning this is an unspecified boundary condition. I leave this open. Then this is a cat or a wave function, or a state. So this is now the vacuum state. And what it is mathematically is that it's a function that can take on a position QF here at its boundary, at this open boundary condition, and it can give back then the wave function psi of QF. So it's a function, I'll write that down, that takes a position QF, so at this unspecified boundary, at this boundary with unspecified boundary condition, and gives back a complex number. That complex number that it gives back is precisely the wave function psi in QF. So again, psi is a function. It takes on a value QF and gives back a number, which is this contraction. Okay, so now we can move on to QFT. I'm going to have in mind that it's QFT with bosonic fields. If you're interested in fermionic fields, then I can refer you as a first reference again to Polchinski, and then. But okay, for our purposes, bosonic fields is fine. So how do we go from quantum mechanics to QFT? So in the Heisenberg picture, your Heisenberg operators become field operators. So if in quantum mechanics you had 1 degree of freedom, now you have a field degree of freedom. And so other than that, the structure is completely the same. So that's why we do quantum mechanics first, so that the structure is clear, and then we can quickly understand the same concept in QFT. So let me write down a state as a path integral in a QFT. So it's the path integral over all my fields this time, where I start from some specified field configuration at minus infinity in Euclidean time. I integrate it all the way, path integrate all the way to t equal to 0, but I leave open where it on which field configuration it ends. So leaving this open with the dot gives me the state. Okay, now this has a pictorial representation. Like this. So if I have a QFT with a Euclidean time direction that I write going upwards, and some space-like dimensions that I can write going in this direction. I'll specify now, for the sake of these pictures, to a two-dimensional QFT with only one space-like direction, which I'll write as x. Okay, so this is. But of course, these pictures. It's just for the sake of these pictures, but of course, it's not restricted to these dimensions. Right, so this is a pictorial representation of the path integration going all the way from minus infinity in Euclidean time, path integrating to t is 0. So I don't know what the English word is. If this part with the stripes is the evolution, sorry? Yeah. Yeah. So you integrate, path integrate all the way from the past Euclidean time, the past in Euclidean time to this time slice at 0t, and where I write a dashed line for where the state this is where the state lives at t is 0, and I write a dashed line representing that I've not fixed the field configuration there, versus this line here below where we have fixed the field configuration to be phi I. Okay, so a solid line will be I fixed a boundary condition. An open boundary condition is a dashed line. But other than that, this is all you need to know about this pictorial representation. This is just what you would write down yourself. Okay. So this is now our unnormalized vacuum state, which is prepared by Euclidean evolution. So prepared by Euclidean path integral evolution over all of the past. So the conclusion here is that a path integral with one set of boundary conditions and one open cut gives us a quantum state. Living at this dashed line. Okay, so if this is my ket, then the bra will be the path integration over the future back to the t is 0 slice. Okay, so let me write it again in formula and in this pictorial notation. So you start integrating from an unspecified field configuration at 0 time and you evolve it to future infinity where you have a field configuration fixed as a boundary condition. That is the bra. Well, maybe I haven't mentioned, but typically you wouldn't actually write these boundary conditions, phi f and phi I, precisely because they're not important. Because you're integrating over an infinite range of Euclidean time, this information, what this actual boundary condition was, does not really play a role. So it goes into what these QF independent factors were upstairs. And I've removed them and was satisfied with this being an unnormalized state. So typically, you would not write this boundary condition phi I and phi f because it's not too important exactly which configuration this is. It's just important that it's a closed line, that there is some boundary condition there. Right, okay, so this means I have to wash the boards. Yeah, of course, yeah, I didn't mention that you should, but yes, yeah.
I'm struggling to understand the Euclidean time, so it looks
Yeah.
first like a mathematical trick.
Yeah.
And then you can like suppress some terms. Like
Right, yeah, yeah.
Does it have any physical significance to take this other time, like this rotation? Does it have any physical interpretation or any physical reasoning what that means?
Well, we'll get to a physical interpretation later in terms of thermal quantum field theory. And for that, it's important to look at Euclidean time evolution. Just mathematically in QFT, it's a matter of discussing also the Euclidean amplitudes and different types of correlators. But for us, the actual physical interpretation will be in terms of thermal physics. And this is something that we'll get to, yeah. Okay, let me start with these left boards. Okay, Okay, so before I continue with the rest of the notation, so going to, so we've discussed the pictorial notation for a bra, for a cat, and then we'll discuss density matrices. Before I do that, let me just add that you can also further evolve the state that we've prepared by path integral evolution in the Euclidean time direction. You can further evolve this in Lorenzian time. So once you hit t is 0, this is the place where Lorenzian and Euclidean time meet. And so from here, the state can be further evolved in our Lorenzian time. So in this case, you would start from an initial Lorenzian time, which is 0. But in general, you could just define an object which is a wave function. Let me put Lorenzian here to distinguish it from our vacuum state there. You can define it as this object of the path integral from some initial configuration to some final configuration, but now evolving in Lorenzian time. And I'm adding this here at this point mainly as a comment because it's for this object that that the reference. So let me write down. So it's a paper from '94 by Larsen and Wilczek. They check that this object satisfies a Schrödinger equation. So if you had still any doubts that this is a wave function, you can go to this reference. Let me put in one line what they prove, but without the steps in between. So they show that this satisfies Schrödinger equation in the sense that if you take the derivative of this object with respect to time, so time would be the time where this configuration lives, which is Tf. So you take the derivative of your wave function with respect to time, which would be, in this notation, the variation with respect to final time of the path integral e to the is. Let me not write the whole thing with the boundary conditions. So what they show is, based on how this object changes under coordinate transformations, you can write. So that here there's some reasoning that I'm not including because it would take too long. But based on how this object transforms under coordinate transformations, which involves the stress tensor of your QFT by the stress tensor definition. This is something we'll come back to, and then maybe at that time it will be more clear to go back to this reference and understand these dots in between. But they show that taking the time derivative gives you this, which you can interpret as the Hamiltonian acting on this wave function. Okay, so we can have a break in about 2 minutes. Let me add one more thing. Which is going back to our prepared vacuum state psi. So I've written the pictorial notation for the state. Let me now write the pictorial notation for the wave functional, which is the state that has taken on as a boundary condition a specific final field configuration. So this we can write as the wave functional, sorry, not Q, but in phi f. Okay, so let me remind you first what the notation was for the cat, which was this. So this would be for this object, and the statement is that it can take on a field configuration at the dashed line, meaning you fill up this dashed line, you've added the actual boundary condition, to be phi f, and that gives you back a number. So a box that has no dashed lines left is a number. If there's any dashed lines, then there's still some slots left where you can insert field configurations as boundary conditions on your path integral. Okay, so pictorially, this phi f would be like a bra that you can glue into your psi to close off this dashed line. I want to erase that though. So yes, pictorially by gluing in the bra phi f on the upper dashed line. And then similarly, if I started from the bra vacuum state, this is now an object that can take on an initial boundary condition. So if my bra was this with a dashed line here at 0, this would be this object. And then I can glue in a cat here as a boundary condition at t is 0. Again, giving me just a box which is a number. Okay, so I think that's a good time to quit for a break, and then we'll discuss the density matrix when we come back. Yeah, thank you. It's just I have to add something to the part that that we ended with. So okay, let me not make this comment now. Right, so we understand states as cats and bras, the pictorial path integral presentation of them, and we understand that if we close this this dashed line with an actual field configuration as a boundary condition, then we get the wave functionals. So now in field theory, these are not wave functions, but wave functionals. This is just the one thing that I forgot to add here. Okay, a wave functional. Okay, and so next on the list of understanding these pictures is the density matrix. The density matrix rho for our state that we've prepared by Euclidean time evolution is just the cat times the bra. So the way you pictorially present this is just by drawing these two things. You have the cat, you have the bra. So this would be psi, and this would be psi like this. This is infinite Euclidean time. This is minus infinity. And these are both at 0, these dashed lines. But you typically split them into 0 plus line and a 0 minus line. Okay, 0 plus, 0 minus. Okay, the reason you don't have these lines actually coincident is because this notation is supposed to remind you what kind of object the density you're drawing. So what, in this case, the density matrix is. The density matrix is a matrix. It has 2 slots where you can add a field configuration as a boundary condition, as opposed to the cat only having 1 slot, i.e. 1 dashed line. So 2 open slots available because it's a matrix. And so if you provide actual boundary conditions at these open slots, then you will get the matrix elements of that density matrix. So the matrix elements are rho contracted with some field configuration phi prime on this side, and some field configuration phi at the other side. So this would be phi, psi, psi, phi prime. And so the picture is that you've closed these dashed lines with this being phi psi. So this line is closed with phi. So with a bra, and this line here is closed with a phi prime, because the whole upper part of this diagram is the number, namely the box psi phi prime. It's this part. So the whole thing you can write as phi prime indices on the density matrix to show that these are the phi prime matrix elements. Okay, and the only thing to remember here is the order of where phi and phi prime are. So it's clear coming from this picture. So but phi prime is here on the upper line. Okay, so this is our density matrix. Now let's take the trace of the density matrix. Questions? Ah, sorry, yes?
What is it that tells you that this, the phi ket and phi bra are the same state? You see what I mean?
No, I don't see what you mean, because they're not the same. They're different field configurations. Phi prime and phi are different field configurations that I choose at will.
No, sorry, the psi ket
Psi?
and psi bra, yeah.
Yeah. Yes, they are the bra and cat version of the same state, yes?
But how do you tell that? Do they have the same initial and final boundary conditions? Like, the solid, so each of them has one solid line, right? So you're choosing the same boundary condition?
Right, so in the end, which boundary condition exactly is not too important because it's the unnormalized one, and then the normalized one will not care about the exact boundary condition. But really it's just the cat that is flipped. Well, it's gone now, but on the previous board, it's the flip of this picture. But like I said, I'm not going to actually include here a phi I and a phi f, precisely because we don't care about those numbers. Those don't affect any physics. Good. So we understand the density matrix. Let's take the trace of the density matrix. Okay, let me write it first in a not so correct but more natural notation, thinking of rho as an actual matrix. So the trace would then be the sum of the diagonal components of your matrix. The II component of rho would be the, so in this notation here, would be the object with the phi I and the same phi I contracted here on the right and on the left. So this is what I would write. Well, instead, let's write it in a more correct form, which is that we should integrate over fields instead of summing. And we take the phi diagonal components of our density matrix. So let me put this in brackets. This first line was just to remind you that the trace is just the sum of the diagonal components. Therefore, in our field theory case, it's just the integral over d phi of rho phi. Now, what is this in this notation? So let me take the phi matrix element. So I fix the field configuration phi here on this line and on this line, and I equate them. So this field configuration is equal to this one because I'm interested in the diagonal components of this matrix that I want to sum. So I equate these boundary conditions, and then I integrate over them. This is the pictorial notation of this previous line. And so typically I'll put some marks here that remind you that I'm equating these. Phi and phi should be the same. Then I integrate over them. And then both pictorially and mathematically, it's clear that what you're doing then is gluing these two path integrals. Because at this intermediate time, if you now allow the field configuration at this intermediate time to be any field configuration, this amounts to closing up your path integral there and having a full path integral evolution all the way from minus infinity to infinity. So this is this gluing of path integrals. And it's exactly what we saw when I wrote down this first step of the amplitude to path integral derivation. Because, okay, maybe there's one step in between to see that. So let me write rho as psi. So So to see mathematically that this is this gluing that we talked about previously, these are just numbers or boxes pictorially. So I can move these around. So I can write this as d phi, psi phi, phi psi. Okay. And now you see that this is just a complete set of states in between psi and psi. And so if you remember, if we have an amplitude and we insert a complete set of states at a certain time, that constitutes breaking up your path integral or cutting it, and vice versa. The procedure of sewing or gluing the path integral was exactly that you insert a complete set of states at that time. And so this is exactly what we're doing here. So we're going in this in the direction of sewing or gluing the path integral by equating the phi's and then integrating over them. So this refers back to this complete set of states insertion of before. Okay, so if you write our formula like this, we find that the trace of our density matrix is the vacuum-to-vacuum transition amplitude. This would be 1 if we had a normalized psi, but I've stressed that it's unnormalized, so it's just a number. So the number it is, we'll call it z. And so now we have a pictorial representation of this z as the full path integral from minus infinity in time to future infinity. So this is our Euclidean path integral, which goes over all time, so it's our full Euclidean path integral if you want. So this is okay, and so pictorially, the full Euclidean path integral is just the full evolution from minus infinity to infinity. Okay, yeah.
So I would assume that if I have a partition function and using a trace, like which is has the property of being cyclic, that this should show up in the pictorial notation. But I think you've somehow used your boxes in a way that the cyclicity is just like, it's not directly in the picture, or what am I getting wrong?
Well, so you're thinking of cyclicity because you're gluing two things together, and we'll see later on that sometimes this introduces some cyclicity in your manifold. But here, here it doesn't, because you're just equating phi prime and phi and integrating over them. So you're just gluing here at 0 these two things together, and all you have left is the integration from minus infinity to infinity. The tracing is in taking the phi components of your matrix and integrating over them, or over phi. But we'll come to examples that I think you have in mind. So yes, just to repeat, what we have here is that the trace of the density matrix is equal to the vacuum-to-vacuum transition amplitude is equal to the full Euclidean path integral, which pictorially is this. Okay. So let me write that conclusion in the following form, that the vacuum-to-vacuum transition amplitude is equal to the full path integral, in which case I won't actually bother to add conditions on this integral, because it's the full one. So this is z. And so one final thing about this, this pictorial notation is that we can also add operator insertions in here. So let me first write the line, because maybe it's easier to read it from right to left. Okay, so let me do that and read it from right to left. So let me add two operator insertions here on this in this path integral. So pictorially, it would just be an operator here at some time and space location, an operator at some time and space location. So an O in x1 and an O in x2, where now x is referring to t comma x, vectorial x. Okay. In terms of the path integral, this is just taking the path integral and adding here an O in x1 and an O in x2. This is what is meant by this pictorial notation, I mean. And you will write this as, in this notation, and call it the correlator or correlation function of these operators. This is what you do. And then going back from the path integral formalism to the Heisenberg amplitude formalism, a correlator can be written as the vacuum expectation value of the time-ordered product of those operators. And now I'm adding back the hats on these operators because they are now Heisenberg operators. Compared to here, under the integral, there's no hats. These O's are just inserted there, and under the integral, you can put them where you want. But the nature of the path integral makes sure that this time ordering in this notation automatically appears. Yeah?
In the pictorial representation, each point in the box would be a field, no? How can I think of
Yeah.
point being an operator and not a field?
Yeah, so these are fields, yes. So this fields, this is precisely that point. They are fields O in X and O in X2. It's in going from this path integral form to the Heisenberg amplitude form that they take on the interpretation of Heisenberg operators. So again, this step is Polchinski Appendix A, for example. Okay. Yeah.
So these operators, are they functionals of the fields and then evaluated at the space endpoints x1 and x2?
Yeah, these operators, yeah, exactly. They can be any fields in your system. So they can be some combination of your phi's, what I called phi, let's say. Yeah, yeah. Yeah, I'm keeping this very general. Yeah. Good. But yeah, okay, so this concludes the pictorial notation for wave functionals and density matrices based on understanding that the vacuum state can be prepared from Euclidean path integral evolution. So that's that. And maybe I erase this so I can... Okay, and so now for the second part of the discussion, we come to the concept of entropy. So first I want to say some general things about entropy, and then how the general definition can be applied in the context of a two-dimensional CFT to define something called, originally, let's say, called geometric entropy, but later on called entanglement entropy. So a fundamental measure for entropy is the von Neumann entropy, which arises in the context of statistical physics, and it gives you some measure for the indeterminacy of your system, or the lack of resolution of your system. So the context in which you've seen this would be a statistical ensemble with some rho, where rho would be a probability distribution in a classical theory or a density matrix quantum mechanically. And so as soon as you have a rho like this, so as soon as you have a probability distribution, you can talk about a von Neumann entropy associated with that. So the von Neumann entropy is then defined as minus the trace of rho log rho. And I'm now adding hats to this rho because the von Neumann entropy is defined in terms of the normalized density matrix or probability distribution. Okay, so this rho hat is rho over trace rho is the normalized one. Okay, so you can check that this agrees with the concepts of entropy that you know from statistical physics. So let's quickly do that. So you can consider a microcanonical ensemble, so an EVN system. In which every microstates are equally probable at a given energy. So here this omega is the accessible phase space volume classically, or it's the available microstates at a given energy quantum mechanically. So because this is a closed system, you just have this this equally probable measure, and if you insert this into the definition for the von Neumann entropy, you will find indeed that the entropy is just the log of omega. So this might seem more familiar if you bring back the Boltzmann constant. Okay, but the Boltzmann constant we don't write, it's 1. But what you find is a von Neumann entropy, which is an energy-dependent entropy, as it should in this EVN system. And so the other type of ensemble that we can consider is a canonical ensemble, so a TVN system or an open system, in which your density matrix is the thermal density matrix, but normalized. So I'm already introducing this notation rho thermal because we'll use it later when we talk about thermal entropy. So it's equal to e to the minus beta h over trace e to the minus beta h, or e to the minus beta h over z of beta. This z of beta is the partition function of your thermal system, okay? So for this thermal density matrix, again, if you just plug it in to the von Neumann entropy definition, you will find an entropy which you can write as 1 minus beta d beta of log of the partition function. So this is basically FSE minus TS, rewritten for S. So this is the standard formula that you will have seen in statistical physics for thermal entropy. So it's an S that is temperature dependent. Of course, beta is the inverse temperature. And so in the limit of large n, this entropy and this entropy will be the same for E, the average energy then. So these are in the thermodynamic limit, where n goes to infinity, these will become the same entropy. Right. So this was just to remind you of the concept of von Neumann entropy, which is the definition of an entropy as soon as you have a probability distribution. Then you can define that entropy as some measure for the lack of resolution of your system. And so we can apply this definition of von Neumann entropy now in the context of two-dimensional CFT specifically, to define something called geometric entropy. So this is what we want to do next. Okay, so for that, let's consider as a setup a two-dimensional CFT, more precisely 1 plus 1 dimensional. So you have an x direction and you have a Lorenzian time direction. So it's a system with a Euclidean path integral z given by d phi e to the minus I. Where the action where the action is just a Lagrangian for those fields integrated over the x direction and the Euclidean time direction, because it's the Euclidean path integral that we're now writing down. Meaning you basically integrate over the complex plane that x and Euclidean time span. Okay, and now let's consider some constant time slice. So we have our 1 + 1 dimensional CFT. My constant time slice I will choose at t is 0 for simplicity. So it's this slice. Okay, I've chosen this constant time slice. And next I will bipartition this system into 2 geometric regions. So I will choose spatial region A. And I will call everything else on this constant time slice A bar. So all the rest is A bar. So you bipartition this constant time slice geometrically into a spatial region A and all the rest, which you call the complement A bar. As you do this bipartitioning, you're assuming that you can factorize your Hilbert space into those regions, in Hilbert spaces over those regions A and A bar. So this is a complicated assumption that there's a lot of literature on this, but I will just assume that we are dealing with quantum field theories where this is allowed. Okay, so let me make my region A a bit more clear. This is my region A. And next I want to consider an observer that only has access to that region A and not to the complementary region A bar. And so this observer will measure the system to be in a state which is not the full density matrix, but is the reduced density matrix, which is obtained from the full density matrix by tracing out the degrees of freedom in the complementary region that this observer does not have access to. Okay, so this observer measures a reduced density matrix. And so in general, this will be a mixed density matrix representing a mixed state. So it will be of this form with the sum of the probabilities equal to 1. So instead of just being a psi, like we have for a pure state, and so pure density matrix, if you take a pure density matrix, which this rho is, but I forgot to say, sorry, that I'm assuming this CFT is prepared in the vacuum state. This should have gone here somewhere, okay. Yeah, sorry. So the setup is a 1 + 1 dimensional CFT with this Euclidean path integral. We assume that it's prepared in the vacuum state by this Euclidean evolution. This means that the density matrix of our system is this one. And then we go on and bipartition it, and we look at what an observer that only has access to one spatial region A measures. And what it will measure is this is not the full density matrix, but the reduced one, and where rho is actually a pure density matrix associated with a pure state. The reduced density matrix in general will be mixed. Okay. And so this observer has less information about the system than a regular observer that has access to the full system. So this lack of information from the point of view of this observer is quantified by an entropy. Namely, the von Neumann entropy of this reduced density matrix. Where again, I'm adding hats, because in the von Neumann definition, I have to use the normalized density matrix. So my rho hat is actually the reduced density matrix normalized with the trace of the reduced density matrix. And so this object that quantifies the lack of information that this red observer in A has is called the geometric entropy. Or the entanglement entropy of region A. So in the notation, I will keep this A to remind you that this is the entanglement of region A. It's the geometric entropy associated with this, with an observer that only has access to region A. Okay, and so to understand what this object measures, how it measures this lack of information, we can quickly discuss when it vanishes. That will teach us about what it's measuring when it doesn't vanish. So when is SA equal to 0? So for this, we can use that in general, a von Neumann entropy will vanish for a pure state. So purity you can check by checking that the trace of rho squared is equal to the trace of rho. And if this is the case, then it's almost immediate from the definition of the von Neumann entropy here that this will impose that the von Neumann entropy vanishes in that case, because you can't have twice the entropy being equal to the entropy without it being 0. Good. So we know that SA will vanish when rho A is a pure state. So I've just told you that in general it's a mixed state because when you integrate out degrees of freedom from your pure density matrix, you will be left with an ensemble of states. But in some cases, this rho A will become pure again. So let's discuss those cases. The first one, so SA will be 0 when rho A is pure, because of this. And so the first instance in which rho A becomes pure is when the region A just becomes equal to the size of the system again. Because then your observer gradually has more and more access to the system till finally it knows about the full system. meaning that in that case, rho A just becomes the original pure density matrix for the full system again. So that's the first case in which rho A will be pure. So it's the case in which the observer has access again to the full system in the limit that the complement of your region A becomes empty. So what we learn from this is that this geometric entropy SA indeed measures an amount of missing information from the point of view of this observer. Because if it has access to the full system, it's 0. The less access it has, the less information. So SA measures the amount of missing information from the point of view of this observer. Then a second instance in which rho A is pure is when your original state, psi, the vacuum state, is factorizable. So if the state in which we prepared our CFT, if that state can be factorized over those two regions into a state in A times a state in A bar, then you can quickly check that just tracing over A bar of the pure density matrix rho will just give you a remaining pure density matrix for psi A. Right, so this is the second instance in which SA vanishes, and this one teaches us that this geometric entropy is a measure for the amount of entanglement between degrees of freedom in A and those in A bar. Because if there's no entanglement, that means that your state can be factorized. And so as soon as you have entanglement, you go away from 0. So SA measures the amount of entanglement between degrees of freedom in A and degrees of freedom in A bar in the state psi of your CFT. All right. Oh. Right, so I just saw the clock, so it's actually 12. Let's see.
Is there something that you want to finish?
Right, let me just finish this page. It's really very minor. Yeah, sorry, I think I went a bit too slow. Okay, but we've introduced the definition of the geometric entropy or entanglement entropy of region A. And so we introduced it as minus trace rho log rho. And there's many expressions, equivalent expressions that you can use for this definition. Right, sorry, yeah, thank you. There's many equivalent expressions that you can use for this definition, and this is what the first exercise will be about, to rewrite this. And so my favorite definition to use, which is an equivalent expression of this, is 1 minus n dn log zn in the limit that n goes to 1, where zn is the trace of the nth power of the reduced density matrix. Okay, this is something that we'll check in the exercises, that how you can go from this line to this line. The reason I like this so this is actually the definition for the von Neumann or geometric entropy that we'll use in the next lectures. The reason it's my favorite is because it shows this resemblance to the thermal entropy form, which is 1 minus beta d beta of log z of beta. And so there's a reason why this resembles this, and this is what we'll discuss in the next lectures. But for now, this is a very separate thing. It's this geometric entropy which takes this form, where Zn is this notation that you introduce for this object, the trace of the reduced density matrix to the nth power. This object is called Z sub n of A, I think. Yeah, it's called Z sub n of A in, for example, the Calabrese review of CFT entanglement. And that notation makes more clear that this is an object that you define after introducing a region A. And I just want to stress that this is the same thing, but that I've lost in my notation, I've lost the information that this is referring to region A, but it's always there. So every time I write a Zn, it's an object that knows about this region A already. And so we'll use this definition to calculate the geometric entropy in a two-dimensional CFT. Using this definition means that what we should calculate to start with is this object Z of n, and then go on and plug that into this formula. So this is what we'll do next, is make sense of what this object Z of n is, which means constructing it and then plugging it back into that definition. But that's for tomorrow then, yeah.